Hello Panthray, and welcome to our new video. Today I will be talking about creeping flow around rotating sphere for low Reynolds numbers. Reynolds number is defined by density times velocity, characteristic velocity, times the length, and divided by eta. The sphere is submerged in a fluid and the sphere is rotating. Its radius is r, and when the rotating sphere is rotating, the fluid is rotating with the sphere. And if in the video on on the derivation of the moment when the fluid is basically this situation, we have forgot the Reynolds number at all. We have forgot the inertial terms. But real fluid, when the fluid is rotating, it has inertia, so it means that there is a centrifugal force pushing the fluid upwards, so it's going to move in spirals out. But from the conservation of mass, the fluid which goes out must go in, so from the poles there is an additional fluid pumping into the system, and it's like a black hole, but the other way, the opposite way, time reversed. So this is the creeping flow around rotating sphere, and we will derive the equations. The pressure is basically this is the pressure. Rho is, remember here, rho is cylindrical radial distance, and omega is angular velocity. Z is this direction is the direction of z unit vector, and again its direction of rotation. And this is the velocity field, and we will derive this also. This term is the first term, the first term in the series. The method will be a domain decomposition, again as I've used in the video on the Olsen approximation. So let us start, and we will start with basic equations. The first basic equation is this. It's the conservation equation, which reads divergence of the velocity field is 0. This is the first equation. The second equation is simple, again, because we are repeating ourselves, because it's the same like in other videos. The second is momentum balance equation. So here rho is the density of the fluid, and basically mass times acceleration equals force. The forces, and these are this divergence of the volume forces and the surface forces. Then material equation. The equation, we will be dealing with Newtonian fluid, and for Newtonian fluids this holds for the stress tensor. So this is the stress tensor for Newtonian fluid. Next, if we substitute in this kind of constitutional relation to this equation of momentum balance, we will get Navier-Stokes equations. Again, we will be treating the problem as stationary, or the time, there is no time component, so v with respect to t is 0, p with respect to t is also 0, these are the zeros. So this is going to be rho v dot gradient of v, and this is equal to minus gradient of p, because there are no internal forces, we will be assuming, plus this is 0 due to this term, plus eta dynamic viscosity Laplacian v. Then what next? Again, this is the equation we will be solving, but for clarification, this is rho, or density, and this is not. For this, we will divide the equation by etas again, and we will define alpha as new coefficient. and this is the equation after dividing by dynamical viscosity, which is this. And for us, alpha will be defined as density of the fluid divided by viscosity, and we have defined Reynolds number like as the density times characteristic velocity, which we will stick to a times omega, the velocity on the equator of the sphere, times a, which is the radius of the sphere. So this is going to be, if you can see, a Reynolds number divided by omega a squared. This is this correspondence. So this is the equation we will be solving. It's basically a partial differential equation, non-linear, because there is the square term or the multiplication of v's on the left hand side. But again, we will be using a domain decomposition or perturbation series. A domain decomposition. First note that we will use a domain decomposition on the equation of the Navier-Stokes itself. We are not making any assumption that there is V infinity or something like that, as in the Ocean case for laminar flow around sphere, when there is V infinity flow in the z direction. So this is the first assumption we are making. Oh, we are making none of the assumptions on this term. So we will substitute in a domain decomposition and the parameter of perturbation, or the perturbation series with comparison of coefficients. So this is the basic domain series domain decomposition method. So we will write this as the first term. Velocity should be not so different than the velocity we have found earlier in the video of the rotation, or the rotating sphere. So you can check it out. And this is the velocity. So plus there is another term proportional to alpha, which is the parameter of a domain decomposition, and there is v1, some function which we don't know yet, and for the pressure like the same. But in this case you already know that p0 is 0, or p infinity if you want. So this is alpha p p1. What about the boundary conditions? We have to assure that the velocity at infinity vanishes. So the first boundary condition to this is that v at infinity vanishes, and the v at r is equal to a vanishes because there is no slip condition. Also the pressure at r is equal to infinity we will assume to be 0. Again, for this case, if we decompose velocity as v0 plus alpha times v1, this condition, this is false condition. This should be rotation of the sphere. So the velocity at r is equal to a is rho times omega. The common formula for mechanics in the first class of the high school or something like that, even elementary school. Next, we will so stick with this boundary condition for v, and these are satisfied for v0 because v0 is the solution for the non-perturbed problem. So this must be 0 at r is equal to a. So for v1 there is boundary condition r at equal to a is 0, and for v1 r is approaching infinity is 0. Again for p1 is 0 for infinity, and even if there was a pressure at infinity, this must be 0 because this is the pressure at infinity, but there is none. We will assume that this is none of pressure at infinity, so this is constant, and the constant is 0. Next, if we substitute in this solution to this equation, the first term will vanish because in alpha term, alpha to the 0th power, because basically it's a solution for non-perturbed problem, and the second we will read this equation. It reads v0 dot gradient of v0, it's equal to minus 1 over eta gradient of v1 plus gradient or Laplacian of v1. This is the equation we will be solving now. It's the first approximation in the aluminum decomposition method. First approximant v1 and p. Now, firstly, we can compute this, because it's easy to compute this, because there is an explicit expression for the left-hand side, and it's very easy. It's a very easy one. So we can compute this left-hand side, because it's basically v0, which is v0 we have found. v0 is this. Rho omega a to the cube divided by r cubed, and phi v0, rho omega I cubed divided by r cubed times phi hat dot product, and there is also the same, we will write this as the same factor, and this is going to be this. And again, as you notice, many terms will vanish, because the nabla is acting on rho, and when nabla is acting on rho, there should be rho hat, but rho hat will vanish with this, because the product there, these are the perpendicular vectors. Again, there is nabla acting on this, the r hat will pop out, so it's again 0, so nabla has to apply on this, only this and only this. For this purpose we will use our table, and nabla for hat, phi hat vector is minus 1 over rho times nabla, phi hat rho hat. So this is minus 1 over rho r phi hat rho hat, so this means it is rho times rho divided by rho. It's rho to the first power, a to the sixth power, r to the sixth power, and there is this dot product is 0, because these vectors are orthonormal. So this is equal to minus a to the sixth power omega squared divided by r to the sixth power times rho hat. This is the equation for this. And this is true for any function v0 which is symmetrical around phi axis and has only phi component. So you can substitute in here this general form, and again v is a function of r and theta, for example. Again, we can use any two combinations from this chart except phi. So, and if you substitute in the general form, this is going to be 1 minus rho v0 squared, and this is true for any this kind of function. This is, I think this is called something like the Graham's theorem, or G. It's named after G, but I don't remember. Gertzling or never mind. But there is a theorem related to this. It's basically dealing with vorticities and something like that. But I will skip this information. Next, we can substitute in here, but you will see that there is pressure and there is V1. We'll be looking for solution for V1, and then it's basically a correction to this kind of flow. This is the first term, the zeroth term. The streamlines are circles, but if we add the correction, it's going to look like this. It's basically a flow from the north or the south pole, and the circulated spreading across the plane z is equal to 0 in the spiral fashion, like in a reversed black hole. Doing this, we can assume. Oh, we can assume later this. I will assume something later, but again, if this equation has to be satisfied, one can find the solution for V1 as a curl of some vector field 1, for example. And if you take the curl of this equation, you will get this curl of this, which is this is minus a to the 6th power omega squared curl of 1 over r to the 6th power rho hat is equal to, this is 0 because curl of gradient is 0. This is a formula, and this is curl of the gradient, and this is curl. You can switch the Laplacian with the curl. Oh, this is not gradient, this is Laplacian, because Laplacian is like a scalar operator, so it's Laplacian and curl, and the curl, as you know, it's Laplacian minus gradient of divergence. So this is going to be Laplacian of Laplacian squared of psi 1 vector minus Laplacian of the curl, Laplacian of gradient of divergence of psi 1. This is the equation we will be solving, but let us first assume that the correction I've mentioned here in this picture will produce this picture is actually symmetrical around the axis. Yes, it is symmetrical always, but I will assume that it lies in perpendicular plane. What it means that any flow is not curved. There is no need for the flow to be curved, because the curved streamline can be achieved by curving this field for V0 only. So I can assume that the velocity field will be the function only. This is assumption I will be making only two variables, for example rho and r, and there is phi component. There is not phi component. This is phi. This is r component plus there is actually no phi component. I've told you already, but and there is, for example, rho component and rho, for example. These are two vectors which lies in the plane in constant, and they are getting from the north pole to the south pole, and again to north pole to spread out, and from the south pole to spread out. And the curving is from the V0, so it's going to be like this. This is first curved in this direction, and the second is curved in the same direction. I think in this one, the same direction, but I'm not sure. Yes, this is the same direction, so it's curved. Both are curved in the same way. So I will assume this, and if this is true, then again you can see the video on the Stokes flow, and this reasoning will lead us to this form of for the psi function. Basically it is only a phi component, and phi, it's a function only of rho and r. This will produce this assumption. And if this is true, then the gradient or the divergence of phi 1 vector is 0 basically, because this is proportional to the sum of vectors in the plane. For phi is constant, time dot product with this, which is 0, and the divergence of this is also 0, so this is 0. And when this is 0, this is 0 actually. And maybe there is a mistake, because there should be a minus sign, I'm sorry, and there is plus sign. There is a plus sign. So next, again, now we will compute these terms. So this is general equation, but we will not yet. We will write this form of solution, we will write psi1 is equal to psi1 vector is psi1 times phi vector to this. So we will get, and this is what? This is curl of this, and curl of rho hat is 0 because the table tells us that curl of rho hat is 0, and there is gradient of r to the 6th power, which is plus, there should be plus 6a to the 6th power omega squared over r to the 7th power, and there is r plus, minus will cancel, r cross with rho hat, and this is going to be minus squared 1. If you remember that these vectors lie in the same plane, so the result will be phi vector multiplicand, or some multiplication with the phi hat vector, and this is going to be the sine of the angles. And if we will see and use right hand rule, this is going to be in the direction of phi, and the sine of this angle is cosine of this angle. So sine of pi over 2 minus theta is cosine of theta, and cosine of theta is z over r. So this is going to be and I forgot I think I forgot something. I forgot when I've performed this curl in here, I forgot the term from this. This is the term of rho, and it should be also here. And again, it's 0 because the curl of rho is gradient of rho is rho hat, and rho hat cross product with rho hat is 0. So this should be 6a to the 6th power omega squared over r to, there is z over r, so it's r to the 8th power times rho from this, and there's the rho. There's the rho from this, and times z, and this is going to be minus Laplacian of, and there is phi 1 phi. We will assume this kind of solution. This solution is on this, and this is phi hat. If you perform this Laplacian, you will see this is proportional to phi hat as you can see in the video on the Austen approximation. Next, we will use the formula. So we write to our table in the last video on Austen approximation, and you can clearly see if we assume this kind of solution, which is 0, and there is some function of r, you will get the same result as on the left hand side, but with a different function of r. So I will try to use this as the solution for psi 1, and then you will see what will happen. So the solution guess, so we will guess the solution, and our guess will be this. Our guess will be that phi 1, this is a scalar from here, is 0 s. So this is our scalar, and for the vector it's just multiplied with phi hat. If we compute the Laplacian again, you will see that it's s double prime plus 6s prime over r. So the Laplacian of this is 0 6 double prime plus s double prime plus 6s prime over r times the phi vector, and again I will write for this 0 and some letter, for example t is the function of r, times phi vector. Again, if we perform it again, the second Laplacian or Laplacian square of psi vector is exactly c, and again this is the same form, so it should be t double prime plus 6t prime over r times phi hat. And this we have to equate with this solution. So it's minus 6a to the 6th power omega squared over r to the 8th power times z times 0 times phi hat from this. This cancels, or you can multiply it with phi hat to get this equation. T double prime plus 6t prime over r is this. This is only equation for r, and this is Euler equation with non-homogeneous Euler equation with the right hand side. Characteristic polynomial is very easy to write, because you can try the solution r to the lambda power, and this will pop up, lambda times lambda minus 1 plus 6 lambda. So the solutions of the homogeneous problem with no right hand side are r to the 0th power, or the constant, some constant g, plus h over r to the 5th power, because there is lambda squared minus plus 5 lambda. The roots are minus 5 and 0 respectively. Next, you can clearly see that we have a right hand side, and you can guess the solution already, because it's only r to something, r to the 8th power. So this solution has to be the 2 degrees small, so it has to be r to the minus 6th power, or yeah, I will try my plus, and there is some constant f, for example, divided by r to the 6th power. And if I substitute in, this will vanish, because it's a solution of the homogeneous Euler equation, and this will produce minus 6 times 7, which is plus 42, minus 6 times 6, which is 36, and the result is plus 6. So this is, if we substitute in, this is 6f divided by r to the 8th, so 6f has to be minus 6a is the 6th power times omega squared, blah blah blah. So the result must be t is equal to g plus h over r to the 5th power minus, there's minus, because we have to divide by 6, a to the 6 omega squared over r to the 8th power. So this is the equation for t, but we have to solve it for s, because the s is a physical quantity. So you have to perform the equation again. There is also a right hand side. This is the right hand side. This is trivial. We can already guess the solution, because you have to write this solution as the first one. For example, is some a plus b over r to the 5th power plus the solution from this equation, solution for this right hand side, and you can already guess it, because there is the 1st power and you have raised 2 more, so it's c r to the 2nd power, or r squared, plus this rise to 2 more powers is d over r cubed. And there is also this solution. This has no undefined constant, so you have to again try a solution in the form as plus some constant j divided by r more powers, and there should be, oh, I'm sorry, this is 6 to the 4th power, because it's more power than 6. And if you substitute in here, you will get minus 4 times minus 5, which is 20, and 20 minus 6 times 4, which is 24. So this should be minus 4. So we have to divide this by minus 4. So the solution, and divided by r squared. So the solution will be, this is minus, and this is a to the 6th power omega squared divided by 4r to the fourth power. And again, we have to assure that v1 at infinity will, from the boundary conditions, vanish, and if v1 is proportional to the curl of some vector field psi, and psi is the order of r squared, because there is r squared times cosine times sine, r squared times s, the solution will be of order r times s, so r times s should vanish, or at least should be at the order of 1, because you can always assume that there is a flow which is proportional to alpha coefficient, or gamma in the case of Gaussian flow we have used, and it's in the first power. So the boundary conditions for S are this: S is proportional to 1 over R maximally, so this has to be 0, C is 0, and C is also 0. We don't need A for this purpose, so I will also cross A and cross this term, because S is proportional to 1 over R. So again, because there is no 1 over R term, there is no flow in infinity in the spiral arms. So this is a different case as in the Gaussian solution, because there was flow at infinity going around the sphere, and there was a flow at infinity proportional to constant of Reynolds number, respectively. This is 0, and there is B, and D. So there is D over R to the third power, or let's B to the fifth power, plus D over R cubed. And again, if the velocity should be 0 at the boundary, so this condition is right here, I think. Yes, there it is. The velocity should be 0 at the boundary of the surface of the sphere. So you have to write the boundary conditions, and if velocity is velocity 1 is curl of some psi 1, which is, and the psi 1 is 0 s and phi hat, then it will vanish when s at A is 0 and s prime at A is 0. Again, it's the same condition as before. And if we substitute into this equation, and if we write s at A is equal to 0, A is the radius of the sphere, the derivative of this is 0, you will get the constants. I will leave this exercise for the reader, because it will lead to again to solving two linear equations with two unknowns. It's very easy to do, to handle, and you will arrive at this solution for S. S will be equal to minus for B term to the R to the fifth power, you will get this minus A to the fifth power times omega squared divided by A to the AR to the fifth power. Yeah, this is the, there should be 7. There's 7. 7th power, otherwise it would be no, there's 2 more A's. So it's this 7, and there is plus the term, I'm sorry, minus from D. From the D term will be A to the fifth power omega squared divided by, again, 8 will be the solution to the third power, plus A to the sixth power omega squared divided by 4R cubed. And I'm sorry, no, cubed to the fourth power, because this term is basically this term and I think there is minus sign. No, there is not, because we are dividing by 6, so there is minus, and if you divide it by minus 4, there should be plus sign. So here is plus, and this solution is the right one. So I'm sorry, you have to solve it with this condition for us, otherwise there would be some messing up. It would be incorrect, the incorrect B and D. So this is the solution, the formal solution, and again, you, as in the case in Ocean's flow, as in the case of Stokes flow, you can always, because you can divide it by a factor out, 1 minus A over R, and you will get this factor is A cubed. It can be simplified, factored out, and this is A to R cubed 1 minus A over R squared. This is the solution simplified for S. And if you can compute T from this, because T was defined as the second derivative plus S, 6 times S derivative, and this is you can do this again yourself. This will vanish because it's a solution of homogeneous equation, so there should be only term with r to the fifth power and r to the sixth power, 2 more powers. So these are plus 3a to the fifth power omega squared divided by 4r to the fifth power minus a to the sixth power omega over r to the sixth power. Notice the a's are in the are to the same power as r's. So this is the equation for t. And now we now have complete solution. We had it right here already for the velocity. You have to just take the curl of this, and as you know, psi1 is defined as the complete solution is for the velocity field is then the velocity at 0. You have to substitute in this condition we have made. So this is the composition we have made. So it's this, and it's plus, and this is plus alpha v1 and v1. You can compute the curl of this, but I will not do that. And this is rho omega a cubed over r cubed times phi hat plus alpha, which was, again, you can remember, alpha was a Reynolds number divided by omega r squared, or the density of the fluid divided by dynamical viscosity of the fluid. So this is this, and plus, or there should be a minus from this when we use this decomposition for S. So it's minus Reynolds number times this, 2 a's cancel out, so there is Reynolds number a cubed times omega to the first power because of the Reynolds number divided by a, and there should be curl of 1 over r times r cubed times, because this is not complete solution, because there should be again this is only S, and the complete solution for, because v1 is curl of psi1, and this condition was written right. This is psi1, and we were assuming the solution for velocity here. So this should be the curl of psi1, and psi1 vector field is this. This is rho zs times phi vector hat. So this should be z rho phi vector hat divided by r cubed times 1 minus a over r squared, and this is going to be the solution for the velocity vector field. For Reynolds number is equal to 0 is the same velocity field, because it's 0 is from the decomposition along, and this will match up with this particle equation, and yes, it's the same as we have arrived to. And now for the pressure will be much more difficult. Oh, not so difficult, I thought, because for the pressure it will be not so difficult at all. Pressure. Now for the pressure. We've already seen the equation governing our problem. It's this, or the decomposed problem. The first order of the problem is this. It's basically V0 to the dot product with gradient of V. We will rewrite this equation, and you will see, and put this on the other side and take minus. So for the pressure, 1 over this gradient of pressure, and this is equal to Laplacian of V1 minus V0 dot V0 gradient, and as you know, this is the curl of this is 0. Otherwise, there will be no pressure, because curl of this must be 0. We have solved it for V1, so this is true. Pressure exists, so this should be Laplacian, and again you can, because V1 is the curl of psi1 vector field, you can switch the orders of the scalar operator, because it's derivative with a vector operator, so it's a curl on psi1 vector field plus or minus, oh actually plus, because we've computed this term, and this term was, I think this term was minus 1 minus blah 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 this, and I'm sorry for again, there should be a row again, and there is 1, this is row, this is row, this is the row path, the missing rows, like a heroes, but not so heroic. So this is minus row, row a to the 6th power, omega to the 2nd power divided by r to the 6th power times phi hat, and this is, oh I'm sorry, no, a row again, row hat, because there is also a row hat. Yes, so this is this. And now you have to compute this term, the curl of Laplacian of psi1. Oh, this should be not so bad, because we already know the solution for psi1, because psi1 is in the form of 0, t and phi, and if you compute its curl, oh, Laplacian of phi, actually psi1 is 0 s, and Laplacian of phi is 0 t phi hat. So curl of Laplacian of phi1 vector is curl of this, it's curl of 0 t phi hat, and this is going to be what? There is z hat curl with this, which is minus rho, so it's minus rho hat rho t plus, and there is curl on this, which is z rho hat, curl of this is plus z, so it's z hat, z from this, z hat from this t, and curl of phi hat is basically 1 over rho. You can again check it out with yourself. Curl of phi hat is 1 over rho z hat. So this will vanish, this term, and there will pop up z hat. So it's the same term as this. So there will be two of them times gradient of t, and there should be r cross product with phi. And again, r cross product with phi. Oh, this should be minus theta because it's the negative order in the spherical coordinates. So it's minus z rho t with respect to r derivative times theta hat. And this is 1 over eta times gradient of pressure. Again, if you compute just the minus this actually. Now I will compute just the term from the r component. So I will multiply it with r hat, and this should be what? This should be r hat times this. This should be 0. This will vanish because r hat is perpendicular to theta. So it's gonna be 1 over eta times p1 derivative with respect to rho r r, and this is going to be r hat dot product with this term first we'll manage this term, so it's dot product with this, which is actually r phi, which is cosine of this angle, which is sine of theta, and sine of theta is rho divided by r. So this should be minus rho squared divided by rt, and the dot product with z will do. Oh, there, there is it. There it is written with not this help of the chart, but again you can see that z dot r hat is cosine of this angle and cosine is this, so it's z over r. So it's again plus 2z squared over r times t, and this should be 0, and there is r this, and again this is going to be rho divided by r. So this is minus rho squared a to the 6th power omega squared over r to the 7th power. So this is the equation for the pressure. If we integrate it, we will get the pressure as the function of r, and the pressure as a function as a whole will be this integral of this before with respect to dr plus some function there should be of theta, because if you perform derivative on this you will get 0 also, but this function has to be 0 because there should be no dependence on phi at infinity. So this is 0 and not even constant, because we've assumed this is constant, so the integral has to be performed like the 1 over r terms will not be 1 over integral of 1 over r squared dr should be minus 1 over r, not plus c. This is 0, and we will also force c to be 0 as this term should tend to 0. So, and but rho cannot be integrated with respect to r, but you can imagine that p is the function of, oh, I forgot to mention, the gradient should be done in one coordinate. Oh, it cannot be done in one coordinate system. It can be done in mixed coordinate system like r and rho, z and theta, but I will stick to spherical coordinates, so I will write this. So the gradient should be p with respect to r plus 1 over r, p with respect to theta. So this is this. So this is the reason why there is f with respect to theta, not with respect to rho. It will be easier. Why? Because if you substitute in rho as a function r squared cosine, rho is r times sine, obviously, and z is r cosine of theta. You have to integrate it only with r, because t is function of only r, so the integration will be really easy and you can do it yourself. I will leave it for the exercise. And then remaining terms will be the pressure will be function of r and theta, there should be some signs, and you will again, as in the case of ocean flow, substitute for sign again in this before integration. So this has to be done this way. So this is Z over R again, and if you do that, you will arrive to the equation of the pressure, and the pressure 1, and pressure will be eta a to the 5th power omega squared divided by 4. I am just writing my older results. I've computed it before. Minus 2z squared a minus a. This is the equation for the pressure, and if you substitute in the equation for the pressure right here, and substitute in alpha, which is the Reynolds number, divided by omega a squared, you will get this pressure equation formula. And now short discussion about the forces. The flow is actually symmetric. Flow is actually symmetric around z direction, or the z plane. So this is symmetric. There is one path, there should be another underneath it. Mirror, it's like a mirror image as we draw here. So there should be no force in this direction. Again, we've assumed this particular form of solution for psi. That means that if you will write to the computer this form, this velocity field. Oh, I forgot something very, very important, and it's curl is the curl. There should be a curl. So this is no. Yes, there should be a curl as you have derived, and you can if you take this term and plot it as a 3D vector field, you will see that it looks like this from upper view. And again, it looks like this from the side view. So there is no rotation. The field is actually contained in only phi direction, as you can perform curl of this, but you can see this is only a function of r and rho. So the curl will be, this should be a gradient of r, and there's a component of phi, but if you take a cross product with these results, with this is 0, so there is no phi component perpendicular to these field lines. So the net momentum which will be produced by this force, because it's symmetric, is 0. There is only like a tension. You can compute tension yourself as if you want, and this tension will be not 0 as in the case of the pure rotation. So there will be a tension. So this is the first correction for tension. You can compute it yourself. I will leave this as an exercise. Also there is a shear because the flow is coming from the poles and leaving at the equator. So there should be a moment stays the same. So as before is minus pi a to the cube power omega and eta. As before is the same. There should be no forces acting on the sphere, and this pure creeping flow rotating around sphere. Rotating around sphere, which is also rotated. So this is the solution for the creeping flow around rotating sphere. Again, I will show you the whole paper. So this is all the whole notes, computation, and this is it. And for the pressure. I hope you enjoyed it, and maybe see you next time. So Panthray and goodbye.